The talk today that Nari is going to be presenting to us is such a timely topic, and we're so lucky to have Nari. She's a second generation member of the Institute of World Culture, and her mom and dad are here today, Joe Miller and Kim Miller. We're proud, Nari. We're very pleased, and you'll see why. Nari graduated from San Marcos High School. She went on to Williams College in Williamstown, Massachusetts. Williams is frequently voted the best medium-sized liberal arts college in the United States. Nari majored in both geoscience and chemistry. She was invited into student membership in the International Honor Society for Scientific Research. Is that Sigma Chi?
Xi.
Sigma Xi. Einstein was a member of this society. Hard act to follow. In preparation for her undergraduate thesis, she did unusual research at Professor Mia Cook's Paleo Climate lab at Williams. She studied a new sediment core from the Bering Sea. Her professor was on the ship that collected that sample, and most of her thesis work involved trying to understand the 1,000-year climate patterns in that core. The part of the core she looked at was deposited 150,000 years ago, and so the microfossil shells that she picked out of the layers of the sediment contained chemical clues as to what occurred that long ago. She found that there may have been methane flux from the seafloor on a 1,000-year frequency. Other research projects include excursions to St. John's Island in the Caribbean, 2010. That's when I would have liked to have been on. Ireland, the summer of 2010, and in the Caribbean she worked with Professor Cox, who returns every 5 years to monitor the size and shape of the reef, to count the corals and the seagrasses. She was one of 10 students chosen to work on this project. In the Aran Islands off the west coast of Ireland, the project was to measure the strength of storm waves. These islands have large west-facing limestone cliffs whose rocks tend to break off into massive rectangular blocks. The strongest storm waves then throw these boulders, all sizes of boulders, up on the tops of the cliff, where they form ridges and piles of boulders. When she was there, they were measuring the size of the largest boulders and mapping the ridges. They also compared photos from 2 years before and found that some of the largest boulders had moved. In the area of climate science, Nari has studied weather patterns, sea levels, freshwater issues, along with erosion and habitable climate. Nari says she's interested in the stories of places, rocks, and things. And let's enjoy Nari.
Well, thank you all very much for coming. It's an honor to be here and an honor to share this presentation with you. So,
And let's enjoy Nari.
well, thank you all very much for coming. It's an honor to be here and an honor to share this presentation with you. So, I thought I would do a presentation on climate science, the methods, processes, and current research. I am not a professor. I have an undergraduate degree in geology. So one of the things that I love about geology is how it makes, a very humble, obscure, boring rock, like the one I'm holding. What color is this? Brown. Maybe a little reddish. If you learn about it, though, after the first glance, it becomes a window showing me a landscape where dinosaurs walked on sandy beaches and how those sandy beaches were then buried in an anoxic ocean. This is a magnificent reason for why, so there is a magnificent reason for why this rock looks so shabby. So, it has a beautiful story behind it. And the fact is that it's old. And somehow it got here from the age of the dinosaurs. So, you're welcome to come up later and look at it. And so, as I said, I think of the seminar as a window to spark and feed your thoughts on climate. Help us get a little perspective on how does climate change and why. We know it is different over space, so across the globe, the certain regional climates change, but then the globe as itself has its own climate. And we also know that climate can change over time. So I'd like to, highlight the basic processes behind that allow it to change and why it would stay stable. Okay. That was the motivation. Here we go. How do we know anything? This is scientific knowledge, not a philosophy talk. So I won't go into what the Greek philosophers said, but in science, the goal is to describe nature in an objective manner. And as subjective beings, that can be difficult. So there are checks and balances, in a way, that science goes through with this. The scientific method, especially, is the process by which scientists collectively and over time endeavor to construct an accurate, that is reliable, consistent, and non-arbitrary representation of the world. So this means that a lot of the scientific method is basically you see something interesting, you guess why it's there, and if that is why, then you would expect to see something else. And then then you go look for that something else. And did you find that? Does it support your guess? And then you repeat that. So that's my... And then what kind of knowledge does this process give us? This is different than, I know my friends, I know my family, I know what school I went to. This is experiential, intuitive, emotional. The nature of scientific knowledge, however, is more through our senses. We need to be able to repeat and define these experiences in a way that can, support a hypothesis. So because of this, experiments are very important. They need to be reproducible and show evidence that the hypothesis can explain. For this reason, no theories can be really proved. They can only be disproved. So everything is a working theory that is so far going well, hasn't shown significant data to the opposite. And in English, we use the word error to mean that's wrong. But in science, it's a very important concept where error is asking the scientists to quantify how sure they are and is a necessity for every measurement. This becomes important when comparing different techniques of finding the same data. So which one is more precise? If you don't have a measurement on, both, if I'm measuring the height of a cliff and all I have is a 10-foot pole and then, a measuring tape with 1-inch increments, one of those is going to be more accurate, but the 10-foot pole is only going to give me 10-foot increments. And so if I get an 80-foot measurement, that for both of them, one of them is still more precise than the other. And so error also becomes important when talking about if something is possible. So the phrase within error is something that shows up a lot in casual discussions of science that may be confusing. And this, in fact, means it's within the realm of the guess. So we have a range of possibility, and it's within that range of possibility. It's not that it's within the realm of being wrong. And, error shows up because we can never make a perfectly precise measurement. There are no perfect instruments out there. And so every measurement that we make has some degree of uncertainty. And no measurement can be perfectly precise or accurate. So as technology gets better, though, we can get better data, as in more frequent, smaller error and more reproducible. So this is a chart that shows the difference in in temperature across the world. So the time goes forward to the right. So the present is, at the very end of the orange line on the right, and the past is to the left. Temperature anomaly means how big is this temperature change from this baseline of the 1971-2000 average. So the main point I want you to see here is how the line narrows on the right and is much bigger on the left. The blue shading shows the uncertainty or the error for these measurements in the past. And so in 1940, we got much better technology, and our measurements became much more precise. And, sometimes in climate, we try and use, old records of, someone stuck in their cabin and they write in their journal, this is the biggest snowstorm I've seen since, all my 70 years of life or something. So, the error increases in the past until we have set up the infrastructure to take regular standard measurements.
That basically increased 1 degree, is that what we're talking about here?
Yeah, and then they're showing we do see a trend increasing temperature anomaly. So that's the difference from the average here. So we are seeing a temperature increase in the global temperature.
Is this average for the whole globe in 1 year?
Yeah, I think so. Actually, it might just be the U.S. Yes, so this is the U.S. Okay, so moving on to climate processes. Sorry. One more thing. So in the realm of scientific, the scientific method, it would be really great if we could perform every experiment according to that specific plan for scientific experiments. But in real life, isolating one phenomena, one chemical that you want to trace through its lifetime in the atmosphere, or one plant's lifetime, whatever it is that you're studying, isolating that can be very difficult because Earth's processes do not draw boundaries, and phenomena depend on multiple factors. And often the outputs of some process becomes the input. And so that creates a very complicated feedback in the climate system. So in terms of studying climate, the process tends to be, for the first discovery, it can be, let's go dig up a sediment core and see what's there and see if we can explain it. And then let's go do another one and see if our explanation fits. It depends more on the reproducibility of your questions. Okay. And so when studying climate processes, there are some things that we do know, which, when we talk about climate processes, we're talking about the long-term average weather of the globe. The weather includes temperature, rainfall, and wind patterns, as well as other factors of the ocean that So this includes the atmosphere, the ocean, the cryosphere, which is ice, which lives mostly on the poles, but also there are large ice sheets on Greenland and during certain times on the continents. So we can talk about the local climate, the regional climate, and the global climate. These are, spatially specific ways of talking about climate. There's also we can talk about the climate on scales of a century, as well as on scales of hundreds of years, thousands of years, and millions of years. All of these, have different factors that are the most important for how the climate would change. So when learning about the climate, we first need to understand, we have the sun and we have our Earth. If it weren't for the sun, we would have a very static, frozen place here. So Earth is a dynamic planet. We have the sun's energy streaming in, causing air to expand, stirring up the atmosphere, mixing the ocean with it, and you see all the many more consequences. Life is possible. In answer to the question, we have sunlight streaming in, why doesn't the Earth heat up? The answer is that Earth also loses heat to space. So sunlight goes in, or energy from the sun comes in, heats up the Earth, Earth loses heat to the atmosphere. As long as the input equals the output, then the Earth is going to stay a steady temperature. And so if the Earth traps more heat, then it's going to heat up because the sun's energy is still streaming in. But if it's not letting as much heat out, then do the math. You're going to end up with more heat on the Earth in the biosphere. So the sun's radiation powers this engine that stirs up the atmosphere and ocean. So understanding exactly why does motion come from the sun? This is, you can see, okay, I'm going to try not to blind anybody. Okay, so right here, these are the sun's rays streaming in from the sun, which is off the page. On the equator, which is right here, the sun's rays hit at almost a perpendicular distance. So for every area on the equator, the sun's rays are more frequent than for every area on the upper hemisphere, on any polar, closer to the pole region. Because this Earth's surface is tilted here, we get the sun's rays being less intense on the polar regions. And because of that, because of the higher intensity of solar radiation on the equator, that means that the equator tends to heat up the most, more fast than the polar regions. And when the equator heats up, that means that in the atmosphere, the warm air expands. We know that. And as the warm air expands, it rises. And so it causes a convection current to form all along the equator. And as the warm air expands, it spreads away from the equator while more warm air is also expanding. And so it creates this motion, this bubble, because we have a gradient of energy where there's more energy at the equator and less at the polar regions. And so as the warm cools, as it moves towards the poles, it then begins to sink. And this creates a a cell of atmospheric circulation. So the rotation of the Earth adds some complexity to the atmosphere's circulation, such as the Coriolis effect. You may have heard of this. This is what causes the trade winds and a lot of the tendencies of the Earth to have, mid-latitude deserts like the Sahara. Why is the Mediterranean area more dry? It's because of these atmospheric circulation effects. But what was interesting that I learned while doing some research for this is that Gustav Gaspar Coriolis, who invented the Coriolis effect, did so by, apparently he was doing experiments with cannons, and he discovered this effect by measuring how far the cannonball went in this moving frame of reference. So he was able to sense the Earth's rotation using his cannon experiments. So, the mad scientist to the max here. And, okay, so we have the atmosphere at the equator is warming, and then the ocean as well carries warmth to the poles. So in the ocean, please remember that salty or saline water is more dense than fresh water. There can be varying levels of salinity, and water circulates in the ocean because of temperature and salinity differences. The surface water near the tropics is warmed and moves poleward. When the water evaporates, like in the warm equatorial waters, it leaves behind salt, causing the water to become more salty. And this also applies to cold polar regions where when the ocean water freezes, it leaves behind its own salt. So cold and dense water from the poles is formed during winter ice formation. And you get these massive underground waterfalls from this really cold, briny solution that is rejected from the pure water ice formation on the surface of the ocean during the very cold winter months. And so all this cold, dense brine flows down and covers the bottom layer of the North Atlantic Ocean. They actually name these levels of water, oceanographers do. It's the North Atlantic deep water. And ocean circulation is three-dimensional, and we really don't understand everything we could about it. So it's a very mysterious force, but it is very important in determining climate because the ocean is made up of water, which has can hold more energy than air can, and so it's kind of like an insulating fluid. It allows it can absorb more heat, and then it can exude heat even when the air around it is cold. And so it's kind of like a savings bank for energy. And so the ocean and the atmosphere interact as well. So when we're moving, basically we're moving heat from the equator here to the poles, and this is creating this heat engine, what you may hear about in this great energy budget. But the ocean and the atmosphere interact. The wind over the ocean drives currents, and salt blown into the air can seed or cause clouds. Heat is transferred between them, and rain can dilute the saltiness. So here's a picture of Gustav. This is an image, a compilation of wind measurements taken in 1978 from a satellite. And I thought it was a beautiful picture. It shows the atmosphere over the ocean. You can see North America in the upper right. And you can see these swirling patterns from the Coriolis effect. And you can kind of see where the equator is. You see the the wind's moving away from the equator because it has the expanding warm air masses. And they're all moving to the poles, trying to, warm up the cold poles. And here's a quick diagram. You don't need to read the words, really. It's just showing the ocean's currents right now. And, well, the very basic ones. So there's, since it's a three-dimensional image, they show the upper surface currents and then how they move down into the bottom of the ocean here with the darker purple ones. And so, it's these ribbons twisting and twining and mixing all throughout all the world's oceans. The California coast is right around here. We're getting water from the upper Alaskan region, and it's all very cold. It's come from the deep ocean here, which is cold, moving into Alaska, which is also cold. And so that's why when we go swimming here, it's a little cold. And then over here, there's this nice, warm, equatorial Gulf Stream that bends and just touches, the eastern coast of the U.S., and that's why when you go swimming over there, it's a little nicer, because you're getting this ocean current that moves up there, and then, Okay. So the greenhouse effect. This is the second part of the energy budget, where how does the Earth deal with the heat with the energy from the sun? We know that the atmosphere and the ocean dissipate the energy across the world, which, causes these weather effects that we know about. But the greenhouse effect is a very important one. It keeps the Earth warm, and Earth's surface would be 33 degrees colder Celsius if it did not have the greenhouse effect at all. So the greenhouse effect comes from this layer of gases that surrounds the Earth. And so the Earth receives radiation from the sun, and this radiation, hits the Earth, warms the Earth, and as the Earth, re-radiates this heat into space, its blanket of greenhouse gases, such as carbon dioxide, methane, water, these recapture this heat or this energy, and then they can absorb some of that energy, and then they re-radiate it in all different directions. So what they do is they basically redirect the spaceward heat back towards the Earth to some degree. And so what happens when we increase greenhouse gases? Well, this can get us into trouble because this can, just by looking at what happens to the heat, this can cause more heat to be trapped inside Earth's energy budget, inside the Earth's space core. So as the sun continues to direct energy towards the Earth is letting less and less out, which means that the Earth is going to heat up. And so here we see solar radiation hitting Earth re-emitting this heat, and some of it reaches space directly radiated from Earth, but much of it is redirected, is caught by greenhouse gases, which then radiate it somewhat into space, and a lot of it back to the Earth. And so when studying climate, we need to use different tools. What do we use today? We have climate stations, which often, they measure the temperature on land, the sunlight, amount of sunlight, rain and snowfall, wind speed. Some of them have very specialized equipment to measure like soil CO2, carbon dioxide, to measure microbial activity, the pH of the rain, a lot of different things depending on what specific thing they're trying to measure, but rainfall, temperature, and wind speed can really get us a lot of information just on their own. So that covers monitoring on land. This image is of a buoy, which is in the sea, and it's hard to see, but there's actually someone standing on it. Apparently the rain gauge on top of it wasn't working, and so they sent out the technical help to go fix it. So people have jobs doing that. And so the buoys can be either anchored or they can float freely across the oceans. Scientists use both of them to study ocean currents and rainfall on the ocean, temperature of the water. When I know that there was I think this might have shown up in a book. I don't remember which book though, but there was a shipment of yellow rubber duckies that were going across the Pacific Ocean, and it crashed or something, and the rubber duckies got stranded into the middle of the ocean, and then months and months later, people were finding yellow rubber duckies washing up in Mexico and different places, and scientists realized that they could use this as a way of tracking where the ocean currents went and how long it took them to go there. So there's a lot of creativity in science.
Micro buoys.
Yes,
Free-floating buoys. They're no longer rubber duckies. So
Right.
the scientific paper, we use
Yes.
free-floating
Yes.
Didn't they come from the tsunami in Japan and China? There was that earthquake and all that, and there was the stuff came over. Yeah, wasn't that one of the things, one of the bunches of things that came over, or is that not?
You may be right. I don't remember the detail.
There was.
Yeah.
That's right. You're right.
Yeah.
It said tsunami, but I meant earth. Yeah, there.
Actually, I think it was a container, one of those containers that fell off of the boat.
Okay.
Yeah,
Right.
and broke open.
Mm-hmm. So you've all heard that story, but so we have water from the buoys, and satellites give us images from space, and this is a fairly recent development, so we don't have long-term satellite imagery. It's mostly from 60s and beyond. And then we have weather balloons, which can fly in the air, measure temperature, tell scientists about what particles are in the air. We can also focus our data gathering on certain events and ecosystems, such as hurricanes, coral reefs. Just what we do is characterize certain things, so you can monitor and characterize things, which are basically words for measuring every single tiny little detail that you can. And the equipment that scientists use can be very, very high tech. There are satellites, there are drilling ships for collecting sediment cores, and there are the Est-wing rock hammers, which you can use to hack off a chunk of rock from a mountain, or to break one apart to look at a fresh mineral. So, everything and anything to do what you need to do. I've used plastic buckets that their bottoms have been chopped off and replaced with a clear plastic, and we use those to look at the shallow water in a coral reef. You just stick the bucket on the surface of the water, and it's like a portal. You can look through it. There are a lot of creative things that go on. And so when we're learning about data gathering, not only do we gather the data, but we also have to process it a bit. So it depends on the type of analysis, but you need to make corrections, for example, for the tides if you're measuring sea level height. And you need to, figure out what could the error of the measurements be. Are the measurements the numbers that you actually want to work with? Maybe you're trying to measure how much water is coming out of a river, and what you've done is you have all the necessary measurements, but you need to use the correct equation to, calculate the discharge of the river. And interpreting the data is also important. Just is it the right thing? Is there some systematic bias to what I've collected? Is there something wrong with my experiment? For example, if you're trying to do a political survey and you only survey people in one building, and that building happens to be a preschool, there's something very wrong with your experimental design. You're not going to get a very good standard, robust idea of what people think in whatever city or town you're looking at, unless you're studying the political opinions of preschoolers. So, and when we're talking about data, it's also important to specify, exactly where and when did you get your data, and how long, what range of time are you talking about? Is it just a year? Is it 10 years? Is it 1,000,000 years? All of these things matter. For example, studying, even if they're in the same system, so in a river system, studying how a pebble tumbles in a stream would involve some fluid dynamics, whereas looking at riverbed changes during spring melts would involve more geomorphology and versus, the long-term development of a canyon from the river. These are all the same idea, but looking at different time scales. And so when I talk about time scales, that's kind of what I mean. Is it over a process over a long term or over a short term? And so the equipment we use can vary depending on what we are looking at. And now it seems like science is moving in a more interdisciplinary direction. We're incorporating biology and chemistry and mathematical modeling, physics, a lot of different things, political science into the ways that, people study the climate and talk about it. It's becoming a very, very new type of scientific discipline compared to, I majored in whatever and that's all I know. You're expected to be able to learn about new things. And, okay, so now we can move on to Paleo Climate. It's a very fascinating subject for me because I did my undergraduate thesis learning about the old climate in the Bering Sea. What Paleo Climate has to offer us is a really fascinating array of different stories waiting to be unwrapped and interpreted. We can try and study what factors were associated with warming and cooling events that occurred in the past, and then we can learn about what caused them to actually occur or what caused them to not occur. So we can understand the way Earth works based on looking at the past. And these two images below are examples of tools that people use in Paleo Climate. They're both scanning electron microscope images. I have to make sure I'm not. Okay, so this is a pollen grain. And this is a fragment of a foraminifera shell, which is a microfossil. It's found, they're probably actually growing right around here. This is an image of the Bering Sea during an algae bloom, taken from a satellite. I thought it was a beautiful picture, and I used it as the background. So this is a forum fossil. It's very small. The pollen grains, people study, what kind of pollens are they, pine tree pollen or more lush tree pollens that they find in certain lake sediments or in ice cores. And we can study the chemical signatures of forams right here. And, forams grow in the, well, I'll get into that a little bit later. So the tools that Paleo Climate uses are often ice cores, sediment cores, coral, and tree rings. And all of these have in common is that they grow regularly throughout time, and they keep a record of that as they grow. So ice cores, the snow falls, and the snow continues to accumulate. And so you can count back each layer. And, one layer, 5 feet down was deposited, 100 years ago. It depends on how thick the layers are and where you are. But as you move down ice cores and sediment cores, you get to older and older layers. And so in this way, we have discrete sections that tell us that if we can analyze them using the correct chemical ideas, we can learn about how the climate has changed or why it deposited those specific chemical signals. And with coral also slowly grows, one by one. Tree rings do that too. So what we do in Paleo Climate is we study proxies, which are our way of measuring climate when we can't actually go back there and take the temperature of the ocean. Proxies mirror the changes in climate and can be shown to do so today. So we try and calibrate as best we can the factors that we see, we guess, are changing in the past. So examples of proxies are microbial life. So we can look at what kind of microbes live in the ocean and the equator, and we can say, okay, those like warm waters, this is what they look like. And then we can study a community of microbes in the polar regions and say these microbes seem to like cold water that's more saline. And so we have these two communities, and when they die and fall down to the seafloor, we can find them in the sediment. And if we see a change in the microbial community of sediment cores, then we can recognize each type of microbe. Then we can say, well, maybe they were moving from this type of microbe that likes warm water to this other type of microbe that likes cold water. Why would it do that? Maybe the water turned colder. And so to be more specific about how we use proxies, one that I'm familiar with is called the oxygen isotope ratio. It's used in studying a lot of ocean studies, looking at how the world's oceans have changed temperature over time, and also identifying glacial periods. So the oxygen, as we know, oxygen has a couple different isotopes. Oh, it's fine. Oxygen 18, well, oxygen 16 is the most common, and then there's oxygen 17, which is very, very uncommon, so we don't use it, and oxygen 18, which is the middle-y common one. These numbers indicate the mass of the oxygen atoms. Oxygen 18 has 2 more neutrons, And oxygen-16 has just 16 neutrons than O18, but they both behave like oxygen. They can both form water. And so ocean water has both kinds. And when these oxygens react in chemical reactions, they move through it just as other waters, as other types of oxygen do. And so one way that we can learn about glacial cycles through the oxygen isotope ratio is because since both kinds are in the ocean water, when, as we learned on the equator, when the water is massively evaporated and moisture is put into the atmosphere, both oxygen-18 and oxygen-16, the heavy and the light isotopes, are moved into the atmosphere, and then as this moist air moves to the poles, the heavy ones can't really keep up. They don't have as much energy to stay in a gas phase. And the light water with just oxygen-16 can make it all the way to the poles, where the eventual destination of this air is. And the oxygen-18 tends to rain out more, so if it's ever going to rain along this path with this cloud of the mix of both types of isotopes, the oxygen-18 is going to tend to leave the cloud more often than the oxygen-16. And so in cold times, when it's very cold at the poles, it snows the oxygen-16 out, the final place where, after most of the O18 has left, this oxygen-16 rich snow falls at the poles and is locked into glaciers, ice, because if it's during a cold time, the snow will accumulate and form ice sheets, and it won't flow back into the ocean, where it will mix back to the equator and be re-evaporated into the atmosphere. So during very cold times, we find that the entire ocean becomes enriched in oxygen-18, because this oxygen-16 has made its journey all the way to the poles and is now locked away in these ice sheets. So the O18 is left to rain out, return to the ocean, and continue on. So we actually find a sign of this chemical cycling in the shells of these foraminifera, because the shells of these little micro fossils, when they're alive, they make their shells using the surrounding ocean water, and they incorporate the chemical signal of the water around it. So we can look at the oxygen ratio of the carbonate of the shells, and using chemical equipment like mass spectrometers, we can look at the oxygen isotope ratio of the shells and learn about how whether it was a glacial time or whether it was not a glacial time. So this is an example of an isotope fractionation process. There are many, many, many of these, and this is a very general overview of it. But I think it's very interesting how we can pick out tiny little fossils from, muddy sediments from the Bering Sea and treat them very, very carefully. And we can learn about the values of how much ice there was in the entire world 150,000 years ago. So very, very large perspectives from a very, very small, humble fossil here. And so when we monitor Earth today, we see, well, let me just tell you what this is. This is something I stole from the New York Times, and since I'm attributing the New York Times, it's not actually stealing. But this had a map of where the strongest snowfall was in the eastern U.S. This was taken yesterday, and you can see that these are basically showing the largest snowfalls in Boston and New York in the past 50 years. And whatever happens today and yesterday will show up probably over here. But you can see that, we're looking at extreme events that occur on Earth. Boston had 2, 1970s, and then 3 more recently. And New York has this big wide gap, and then all of these. New York is further south than Boston, so we expect to see more snowfall in Boston than in New York. But we see this big cluster to the right of New York, and this kind of fits with what we've been seeing while we monitor Earth climate today, where we're seeing a higher frequency of more extreme events, which means, we're seeing stronger droughts more frequently, we're seeing stronger hurricanes more frequently. And this relates to the idea of, why are we seeing these? We're seeing these because of the scientific consensus of climate change. And we understand climate change to be because of increasing greenhouse gases in the atmosphere. Those are the main drivers. There are other ones that we're also doing, but when we monitor Earth, I guess I'll show you a video after the break that would relate to this section, but it's a very beautiful video. You can, enjoy it however you want, with your intellect or with just your eyes. One important part of monitoring Earth today is that our technology is the best right now that it has ever been. And so when we put resources into learning about our Earth today using this new technology, it's really, really worth our time. We learn so much about it. And, our satellite images, we have new mathematical ways of counting pixels and assigning, for example, we can use remote sensing to do all kinds of things, including tracking shipping lanes across the world. This is a map of satellite images taken of nitrogen dioxide emissions on Earth. And, the land is grayed out, but on the ocean, you can see a shipping track right there where ships go and they burn fossil fuels and release nitrogen dioxide. And, there's a faint one right there in the Red Sea, too. We probably can't see the ones around China because there's so much pollution there as well. I see a slight one, right along here. But, so we're using satellites to see very, from a removed perspective, a remote perspective, why the results of all these things that we do. There's also farmland use, as I was beginning to talk about before, where we can look at the color of soybean farms from a satellite image and we can count pixels with that certain color and mathematically quantify changes in farmland use. So you can quantify how many more soybean farms are there than there is Amazon forest over the past 5 years. I think this is a very powerful tool where we can learn about Earth, and with very careful observation, we could even see the results of certain changes that we do, that humans have on it. And finally, we can also quantify sea level rise using satellite images and satellite monitoring. So when we predict the future, we try not to use a crystal ball. We try and use what we know. And, I've given you an overview of how we look at things. We look at what we know about the processes of what happens in the climate. We know that there is something called the greenhouse effect, and so as we increase carbon dioxide into the atmosphere, how can we expect the Earth's climate to change? Well, we can use Paleo Climate examples of when carbon dioxide quickly doubled to try and understand, or quickly, increased in a certain amount. We can try and study these past times when this occurred to figure out what will happen to us if we continue, emitting greenhouse gases into the climate. So what we know from our current modeling, or from our current monitoring of the Earth, is that the climate is actually changing. We know that. And there are, we don't know how much. There are a vast array of models. However, the models with the smallest amount of uncertainty predict the largest changes in the oceans, in sea level, in temperature, in weather patterns. And so when we talk about climate change, what am I talking about? I'm talking about major changes in temperature, rainfall, snow, or wind patterns lasting for decades or longer. This may come from natural processes or human activities. And this rate of change is outpacing predictions. Models are undershooting the amount of change that is occurring. So, our models from 10 years ago are undershooting what's actually occurred over the past 10 years. So that's one way that we check models, is a, day by day, oops, too late basis, but we need to, try and figure out how to do this more accurately. There's been, a vast array of different ways of predicting things, using certain factors and not using other factors, and saying this one balances out that one. But in the end, they all show that there is a warming trend. Further change is inevitable. Stronger drivers of change, of climate change, are population, human population. We cut down forests, and we dig up fossil fuels and burn them, and we drink water. We do a lot of things. And often the results of this is that we produce methane, carbon dioxide, and as a feedback that we learned about, one of them is that as the air warms, more ocean water evaporates, and water is also a greenhouse gas. So there's this positive feedback loop of, pushing it towards warming once it's started. And when I, ask about an equilibrium state, this refers to atmosphere, oceans, and the cryosphere, land. But the item in climate that has the most thermal inertia is the ocean, which, as heat goes into it, as I said, it's kind of a savings bank. It can collect a lot of energy and then slowly release it over time. So right now, as the air warms, the atmosphere warms, the ocean is slowly collecting this energy. And even if the atmosphere stops warming, the ocean has a much slower lifespan, and so it a much slower timeline for stopping its warmth, its emitting warmth. So once it becomes warm, it's going to stay that way. It has thermal inertia. And so this is an example of a feedback on a different time scale. So when we're predicting how will things be in 100 years, how will things be in 1,000 years, we need to, the biggest question is, what will humans do right now about greenhouse gas emissions? That is the biggest uncertainty. And I went to a big American Geophysical Union conference in December, and I went to a talk, and they said that very emphatically, like, the biggest unknown that we have right now is, what are we going to do about it? We have all these indications that there is danger, and we're quibbling about how fast are we going to get to 4 or 5 degrees, when in fact the question is, we don't want to be at 4 or 5 degrees increase at all from where we are right now. That could be very disastrous for us. And one of the reasons why it could be disastrous is sea level rise. So we know that the sea level will rise because of global warming, because we have ice caps that will melt, Greenland will melt, and also thermal expansion. As water gets warmer, it expands a tiny bit. And you probably won't notice that when you microwave your coffee cup or make your tea in your teapot, but it will expand, and this becomes significant when you're looking at an ocean full of water. And so sea level rise will also affect coastlines, islands. It causes saltwater intrusion into freshwater aquifers, which basically ruins people's drinking water in coastal areas. And it also affects both human populations and biodiversity populations, like in estuaries on the coasts of the world. Most human beings live on a coast of the ocean, and so this is an interesting fact that's going to affect a lot of people with, if storms increase more frequently and if sea level rises, this causes the severity of storms to also increase. And so, as we're seeing a very rapid change, we're predicting a rapid change, and things will level out eventually, but it may be a lot of pain and suffering along the way. Anyways, I was trying to think of a way to end this much better than that, and other than pain and suffering. And so I think I want to go. I think I want to talk about the background here. This is the black background. This is a background that I used in my senior thesis, and it's an image of the Bering Sea during an algae bloom. And the little microfossils that I was studying were probably growing right down there. That's amidst all the all the algae.
What's the dimensions that we see?
Let's see. I think you can see one of the little islands that are off the tail of Anchorage right there. So there's a very big landmass up here. I I don't know the dimensions exactly.
1,500 miles.
Probably, yeah. And so these are clouds that are in the foreground. And so this, gives us I really like satellite images. They give you a very beautiful, distant sense, of a different perspective of what you see every day. And so these